Imperfections or the defects in the case of solids. Now, what is imperfection or defect? Any departure from perfectly ordered arrangement of the constituent particle in the crystal is called imperfection or defects. When the deviation or irregularity takes place from the ideal arrangement around a point or an atom in the crystalline substance, then the defect is called point defect. Now, the point defects are divided into three parts. It has three types: stoichiometric defects, non-stoichiometric defects, and impurity defects. These are the three types of the point defects. Now, in case of stoichiometric defects, these defects do not disturb the stoichiometry of the solid. They are also called intrinsic or thermodynamic defect. If the imperfection in the crystals are such that the ratio between the cation and anion remain the same as represented by the molecular formula, then we call them as stoichiometric defects. The types of the stoichiometric defect: first, vacancy defect. When some of the lattice sites are vacant, the crystal is said to be the vacancy defect. This results to decrease in the density of the substance. This defect also develops when the substance is heated. Next is interstitial effect, which is a part of stoichiometric. When some constituent particle like that of atom and ion or molecule occupy interstitial site, the crystal is said to be the interstitial defect. This defect increases the density of the substance. Vacancy and interstitial defects are explained only by non-ionic solid. The ionic solid must also always maintain the electrical neutrality, and ionic solid shows the Schottky and Frenkel defect. Now, in case of Schottky and Frenkel defects, first we have to study about in the case of the Frenkel defect. This defect is shown by the ionic solids. The smaller ion, usually cation, is dislocated from its normal site to the interstitial site. It creates a vacancy defect at its original site and interstitial defect at its new location. The Frenkel defect is also called dislocation defect. It does not change the density of the solid. Remember this thing, in Frenkel defect the density will not change. The Frenkel defect is shown by ionic substances in which there is a large difference in the size of the ion. For example, ZnS, silver chloride, AgBr, AgI, due to the small size of zinc and Ag ions. While in case of Schottky defect, the Schottky defect is usually created when vacancy defect is originated in the case of ionic solids. In order to maintain the electrical neutrality, the number of missing cation and anions are equal, then the Schottky defect is created. Suppose if we take AB type of ionic solid having equal number of cation and anion, and equal number of cation and anion are missing from their lattice site, so that the electrical neutrality is maintained, and it is called the Schottky defect. The Schottky defect contains one pair of holes due to missing of one cation and one anion, and the type of the compound which exhibit the Schottky defects are having high coordination number, small difference in the size of the cation and anion. Example: sodium chloride, potassium bromide, AgBr, cesium chloride. Now, effect on density. In case of a Schottky defect, as the number of ions decreases as a result of this defect, the mass decreases whereas the volume remains same, and hence the density of the solid decreases in the case of Schottky defect. Now, in case of non-stoichiometric defects, it will arise as a result of the imperfection in the crystal. The ratio of the cation to the anion become different from that indicated by the ideal chemical formula, then the defects are called non-stoichiometric defect. The non-stoichiometric defects are divided into two parts. Number one, metal excess defect, and number two, that is metal deficiency defect. In metal excess defect, the first one by anion vacancy, and the second by the presence of extra cation in the interstitial site. Now, first we have to discuss about the metal excess defect due to anion vacancy. A negatively ion may be missing from the lattice site, leaving a hole which is occupied by the electron, thereby maintaining the electrical valence. The site containing the electron are thus trapped in the anion vacancies are called F centers. They are responsible for imparting the colorization to the crystal. For example, when NaCl crystal is heated in the atmosphere of sodium vapors, the excess of the sodium atoms deposited on the surface of NaCl, the chloride ion then diffuse to the surface where they combine with the sodium atom, which will become ionized by losing electron. These electron diffuses back into the crystal and occupy the vacant site created by the chloride ion. These electrons absorb some energy of the white light and giving yellow color to the sodium chloride. In the similar way, the excess of lithium in lithium chloride makes it pink color, and excess of potassium in potassium chloride makes it violet color. Now this defect is metal excess defect, which is created by anion vacancy. Now the second metal excess defect is due to the presence of extra cation in the interstitial site. The metal excess defect may also be caused by the extra cation occupying the interstitial site. The electrical utility is maintained by the electron present in another interstitial site. This defect is similar to the Frenkel defect and is found in the crystal having Frenkel defect. For example, when zinc oxide is heated, it loses oxygen and turns yellow due to the following reaction. ZnO on heating change into Zn plus 2 plus half O2 plus 2 electrons. Here the zinc ions thus formed get trapped into the vacant interstitial site and the electrons in the neighboring interstitial sites. The crystal with either type of the metal excess defect contain some free electrons, and such material act as a semiconductors. Now the metal deficiency defect. This defect occurs when the metals show variable valencies, especially in the case of transition metals. The defect usually occurs due to the missing of the cation from its lattice site and the presence of the cation having higher charge in the adjacent lattice site. Examples: FeO, Fes, NiO, in which we are getting the variable valencies of plus 1 and plus 2. And the next defect is known as the impurity defect. This defect arises when the foreign atoms are present at the lattice site in place of the host atoms, or at the vacant interstitial sites. In steel or the carbide of iron, the carbons are present at the interstitial site in the lattice of Fe atoms. The process of adding impurity to a crystal lattice so as to change its property is called doping. Now, doping with electron-rich impurities. As we know that group 14 element like silicon or germanium has 4 electrons in the valence shell, and they are able to form 4 covalent bond with the neighboring atoms. When it is doped with group 15th element like phosphorus and arsenic, the silicon or germanium atom of the lattice site are substituted by the atoms of phosphorus and arsenic. Now, as these atoms have the 5 electrons in the valence shell, after forming 4 normal strong covalent bonds with the neighboring silicon atom, the 5th extra electron is free and get delocalized. These delocalized electron increases the conductivity of the silicon and germanium, as the increase in the conductivity is due to the negatively charged electron The silicon or germanium crystals doped with electron-rich impurity are called N-type semiconductors. Now, when the doping with electron deficient impurities takes place. Now, when 14th group elements, they are doped with 13th group element like boron, aluminum, gallium and silicon. Then the 13th group element have 3 valence electrons. They can form only 3 covalent bonds with the neighboring silicon atom, and thus a hole is created at the site where the 4th electron is missing. This is called electron hole or electron vacancy. An electron from the neighboring atom can jump to fill up this electron hole, but then an electron hole is created at the site from where the electron has jumped, and they are able to create a p-type of semiconductors. Now silicon and germanium doped with electron deficient impurities are able to form p-type semiconductors, while the silicon and germanium, when doped with electron rich impurities, they are able to create n-type of semiconductors. These are the two types of the semiconductors which are created only by the doping process.